So we're going to continue with our previous question. So the previous question, I'm just going to write the constraints that we had. So remember, we had Department A, Department B, and Department C. Department A was 8x plus 10y was less than or equal to 11,000, with 4x plus 10y is equal to 9,000. We had 12x plus 6y is equal to 12,000. Now optimum point, we found it where line A and line B were intersecting. That's where we got our optimum point. Then we say that the two lines that meet where you get the optimum point are the two lines that we call the binding constraints. So here A and B are binding constraints. So it's only at the binding constraints do we get the shadow price. So we can only have a shadow price for line A and line B. So we're going to look at first increasing the 11,000 hours to 11,001, because remember we said shadow price is the extra contribution that we get by having one more of the scarce resource. So let's start with Department A. So if we increase Department A by 1, means we get 8x plus 10y is equal to 11,001. We have 4x plus 10y, it's equal to 9,000. Then we have to solve our equation simultaneously. Remember, solving our equation simultaneously, we said either the x coefficient is the same or the y coefficient is the same. So here already the y coefficient is the same. So what I'll need you to do is I'll need you to solve the equation. So because I've already done that, I'm just going to put down the answers. So here our x will be equal to 500.25 and the y will be equal to 699.9. So that will be our new optimum point. So before it was x is equal to 500 and y is equal to 700. Then I want to find the contribution. So our contribution line was 4x plus 8y. So here we take 4 times 500.25 plus 8 times 699.9. So saying 4 times 500.25, that's 2001, plus 8 times 699.9, so plus the 2001. So our final answer will be 7,600.2. So that will be the new contribution if we have one more hour in Department A. So before our contribution was 7,600 when we found our optimum point, when we use 500 and 700. So if we use the optimum point of 500 and 700, so our contribution was 7,600. So now here, if we have one more hour in Department A, our contribution is increasing by only 20 cents, which means that the shadow price in Department 1 is 20 cents. The shadow price in Department 1 is 20 cents. So that's for Department 1. So we're saying the shadow price for Department 1, the shadow price for Department 1 is 20 cents. Now how we can explain this is, we're saying the shadow price is the increase in contribution if we have one more unit of the scarce resource in Department A. So in Department A, if we had 11,001 hours, our contribution would increase to 7,620 cents. So that's our shadow price. We can explain it again in this way, saying for the hours that we have there in Department A, if we want to get one more hour, we're prepared to pay a premium of 20 cents. That's also what shadow price means. We can pay a premium of 20 cents. So if our hour we spend say $10 per hour. This means that the company is prepared to pay a maximum of $10.20. That's another way of explaining the shadow price. So I'll explain this again. So if we had 1 more hour in Department A, our contribution would increase to 7,620. So it would increase by 20 cents. And then if we want to get that 1 more hour, then it means we are therefore prepared to pay a maximum of 20 cents. Because if you pay more than 20 cents, then our contribution is going to drop below 7,600, because we're only going to get extra contribution of 20 cents. So we're prepared to pay a premium of 20 cents in getting 1 more hour. And let's look at if we do this to Department B. So in Department B, if we increase the hours, it's 4x plus 10y. If we have now 9,001 hours, we have increased the hours by 1. If you also stop the video, you do the simultaneous equation, you notice that you get x as being equal to, so I've already calculated this, $499.75, then y is equal to 700.2. Then we substitute this into our contribution line. Our contribution line is 4 times 499.75 plus 700.2 times 8. So it's 4 times 499.75, which is 1,999 plus 700.2 times 8 plus 1,999. Now contribution here we get it as 7,660. Okay, 7,660. Now what this means is, if we could get 1 more hour in Department B, our contribution would increase by 60 cents. So the shadow price for Department B, the shadow price for Department B is equal to 60 cents. Means when we have 1 more hour in Department B, our contribution will increase by 60 cents. How else we can explain it is, we're saying, if we want 1 more hour in Department B, we're prepared to pay a premium of 60 cents. That's the maximum that we can pay, because we know that that 1 more hour or that 1 extra hour is going to increase our contribution by 60. So there's no way we're going to pay more than 60, because our contribution is only increasing by 60. So for Department B, if we're paying, or if we spend $15 for every hour, then we are prepared to pay a maximum of $15.60. So the shadow price here, we can explain it as the premium, the amount over and above the normal amount that would pay. So it's the premium that would pay to get 1 more hour in Department B. And here, Department C here, because it's a non-binding constraint, it doesn't have a shadow price, because it's a non-binding constraint. It does not have a shadow price, because already we're not fully utilizing the hours in Department C. So to just round off on the sensitivity analysis, we're saying we can only have a shadow price on the binding constraints. The binding constraints are the 2 lines that meet at the optimum point. The rest of the lines are non-binding constraints, and they do not have any shadow price. So that's it on our sensitivity analysis. So you can just go back to try to fully understand this. But on sensitivity analysis, basically we're looking at our shadow price. So we can explain it in 3 ways. 1, the extra contribution that we get if we have 1 more of the scarce resource, or the reduction in contribution if we don't have that resource. And the third one, we say the most important one, we look at what is the premium that we are willing to pay, what is the maximum that we're willing to pay over and above the normal amount that we would pay for the scarce resource. So that's it on sensitivity analysis. We're now going to look at the competitive aspect of linear programming. So we're going to start with question number 123 from the old revision kit. So for those who have the new revision kit, the question will come up on the screen. So in question 123, the requirement says, which of the following equations represent the ISO contribution line? Remember we said on linear programming, when you're using the graphical approach, we have 5 steps. Step 1 was to define our variables. And we said in step 1, what we're just trying to do is we're trying to give the product to the x-axis and the y-axis. So with this question, I'm just going to do it step by step, although they do not require step by step. So if this question had asked for step 1, so which will never be asked, what we're going to do is step 1, we're going to say let product J be the x-axis. Then we say let product L be the y-axis. Or you can have it the other way around. You can say let product L be the x-axis, let product J be the y-axis. That's just basically step 1. We just want to give our product to either the x-axis or the y-axis. So that's why we say for linear programming, we can only use it if we have 2 products, because we can only use the x and the y-axis, only for our syllabus. Then our step 2. So define the objective, or state the objective. Said for our objective, when we look at linear programming, we have 2 objectives. Either want to maximize profits, which is the same as maximizing contribution, because remember fixed costs are constant. So if you maximize contribution, you have also maximized profit. Or the other aim is we want to minimize our cost. So with this question, we're looking at maximizing the contribution. And our step 2, we'll be looking at our contribution line. So yeah, our aim here is to maximize contribution. So we have put 2 products, we have J and we have L. And we need to calculate the contribution for J, and we need to calculate the contribution for L. So we need to calculate contribution for J and for L. Calculate our contribution, we take our selling price per unit, less our variable cost per unit. So for J, we take the 115, which is the selling price, minus the variable cost. Remember, our direct costs, all of them are variable. So let's start with J. I want to find the contribution. The contribution will be 115 minus 20 plus 12 plus 18 plus 14. So we have our direct material, it's a variable cost. Our direct material B is also a variable cost. The skewed labor, it's a variable cost. Then variable overhead is also a variable cost. So we say 20 plus 12, that's 32, plus 18, that's 50, plus 14, that's 64. So we take our 115 minus 64, that will be our contribution. Then we do the same thing for L. For L, the selling price is 120 minus the variable cost is 10 plus 24, which is 34, plus 21, which is 55, plus 18, which gives you 73. So that's for L. So we take 120, so 120 minus 73. So that's how we get our contribution per unit. So we take our 115 minus 64, we get 41. So 115 minus 64, we get 41. That's the contribution. So $41 per unit. We'll do the same thing for L. Say 120 minus 73. 120 minus 73, that will be $47 per unit. So this was our step number 2. Our step number 2, we're looking at the aim of maximizing contribution. Now with our question number 123, it's saying which of the following equations represent the ISO contribution line? We said an ISO contribution line, it's a line similar to the contribution line here. It's a line similar to the contribution line. I mean the line has the same gradient as a contribution line. When we looked at the previous example, so I showed you we drew two lines which were all ISO contribution lines. We noticed that they all slant at the same angle, which means they all have the same gradient. So the line that's going to be ISO contribution line is going to be 41J plus 47L is equal to M. So the answer for number 123 is B. So what's important on step number 2 is we should just be able to calculate the contribution per unit. Contribution per unit at selling price less our variable cost. All our direct costs are variable costs. Then we include things like variable overheads to get our total variable cost. So the answer there for number 123, it's B. Answer for 123, it's B. Now what we're going to look at next now is if the question had asked us to do step 3, which is stating the constraints, how are we going to state the constraints? Now we're going to look at step 3. So remember, step 3 is not asked in the question. We just want to illustrate how are we going to do our step number 3. So step number 3 is we need to state the constraints. Now our constraints in linear programming, we need to state them as inequalities. So that's step number 3. So remember when we started the topic, we looked at an example of an inequality. We said an inequality is different from an equation. Because an inequality, we say in the left hand side either is less than or equal to the right hand side, or the right hand side is less than or equal to the right hand side. With an equation, we say in the left hand side is equal to the right hand side. Now with our question it reads, JRL manufactures two products from different combination of the same resources. Remember, for linear programming in our syllabus, we can only use it for two products. Then we're given the unit selling prices and the unit cost. And goes on to say, for the next 4 weeks, the achievable production level will be reduced due to a shortage of available resources. The resources are expected to be available as follows. Direct material A, there's a question mark. Direct material B, we only have 1,750 kgs. Skilled labor, we only have 1,250 hours. Machine time, we have 2,400 machine hours. So we're going to start with the first constraint, A. We're going to have A, we're going to have B, material A. Material A, material B. We're going to have skilled labor. We're going to have machine time. So under our linear programming, we said we can have 2 or more constraints. So that's what we're looking at here. The company has 4 constraints. But previously, when we did limiting factor analysis, we were only working with 1 limiting factor. So let's start with machine A. So for machine A, we don't know how many, direct material A, we don't know how many kgs they have. But what we do know is, for J we spend $20 on direct material A. So if we spend $20 and each kg costs $10 per kg, it means that we need 2 kgs of J. So we need 2 kgs of J, and we say plus. Then for material L, we spend $10 per unit. Then each kg costs $10. It's $10 per kg. For 1 unit, we're going to spend $10, which means we only need 1 kg of L. So this should be less than or equal to an X amount. We're not told. So I'll repeat this. Now we're stating the constraints. So the constraint, we're saying we cannot exceed an X amount of kgs. But then we know that for us to produce J, we're going to spend $20 on material A. But each kg costs $10 per kg, which means we need 2 kgs of J. So we say 2J. Then we go to L. We say we're going to spend $10 on material L. So we only need 1 kg. So say 2J plus 1L is less than X kgs. We go to B, we do the same thing. For material B, we cannot exceed 1,750 kgs. Then J uses, on J we spend $12 on material B. Each kg costs $6. And this again, it's going to be 2J plus But then on L we spend $24 of material B. So we spend $24 of material B with each material costing $6. This is 4 kgs of L. So in your exam, unlike the example that we did previously, on that example it was just quite simple. We're given how many kgs we needed to use in each department. We're given the hours that we needed to use in each department. So it was quite simple when we looked at our first example. That was just for illustration. In the examiner will not give you the amount of kgs that you need to use, but you just have to figure out by first checking how much are we spending and how much does it cost per kg. We do the same thing for skilled labor. Of course, skilled labor J, we're going to spend $28, but each hour costs us $14 per hour. So that means again we have 2 hours J plus on L we're going to spend $21, but each hour we're going to pay $14 per hour. It means it's 1.5 hours. This should be less than or equal to 1,250. And we go to the last one, which is machine time. So in machine time, if you go to variable overheads, our variable overheads are $4 per machine hour. So we can use that to get our machine time. So for J, we're spending $14 on variable overhead, and each machine hour costs us $4 per hour. So we say 14 divided by 4 is 3,5. So we need 3.5 machine hours of J. Then we go to L. For L, we have $18 that we're spending. Each hour we spend $4, so we say 18 divided by 4. This is 4,5L. These hours should not exceed 2,400. These are machine hours. These are labor hours. These are kgs. So this will be stating our constraints. Now with this question, we're not told if they are demand constraints. So this 4 here, we call this resource constraints, because we're looking at resources. We're looking at material, we're looking at labor hours, we're looking at machine hours. These are resource constraints. But we said we can also have what we call demand constraints. Demand constraints. So we have resource constraints, we have demand constraints, and we also have what we call policy constraints. But for our syllabus, we'll not be looking at policy constraints. Policy constraints, these are constraints that are put on the company by the management. So these are self-imposed constraints. Now example is, when it comes to the hiring policies of some companies, they prefer certain individuals over other individuals. So that's a policy that they use, and sometimes it constrains the organization. It restricts the organization from making more profit. But in our syllabus, we're not going to look at policy constraints. We're going to look at two: resource constraints and demand constraints. So these are our resource constraints. So that will be our step 3. We're looking at our constraints. Now once we have our constraints, we need to now look at step number 4. We need to look at drawing the graph. So number 123, the graph has already been drawn, but I'm just going to show you how did they come up with the graph. How did they draw the graph? So to just show you how they draw the graph, what I want you to look at is the graph that is already drawn. So the graph will come up on your screen, and we're going to use the graph to answer the question, but I'm just going to try to illustrate how did they come up with the graph. So now we're going to look at how they drew the graph. So already on our question, the graph has been drawn, but we came up with the constraint lines on the board with material A, material B, skilled labor, and machine time. So here, just to illustrate, if we go to material B, when J was equal to 0, we said L is 437.5. So that's it for material B. That's the point that we're talking about. Then we can also do the same thing for our machine time. On our machine time, we said when J is equal to 0, L is 533, which is this point. So then they also had on the y-axis, they drew the point. So you notice our scale doesn't go up to this point. So we're just going to illustrate using the x-axis. So in your exam, you'll not be asked to draw the graph. The graph will be drawn. What we just need to do is we need to either look at the optimum point, or we just need to do our ISO contribution line. So either you'll be asked for step 2, step 3, or step 5. Step 4 will not be asked, the drawing of the graph. So here, if you notice, the examiner has given us the ISO contribution line, so we don't have to draw the ISO contribution line. What we just need to do is to indicate the feasible region and the possible points. So we said how we do it is, if we maximize in contribution, we start from the point of origin and we go to the x-axis. The first point that we get to, it's a possible point, and on the y-axis again, the first point here. Then what we need to do is we need to join the points. So we need to join this red dot with this red dot. So how we join them? We have to pass through here and here. So these are our 5 possible points. So point of origin, so this we call it, let's say 1, this is 2, this is 3, 4, this is 5. And what we're now going to do is we take our ruler. So in the exam you need to have a transparent ruler. Just put it on the ISO contribution line on the computer. Then we need to slide it, maintaining the gradient. And the last point to be touched, here it's point number 3. So that will be our optimum point, point number 3. Then we need to look at point number 3 and say which 2 lines intersect at point number 3. So at point number 3 we have material B intersecting with material A. So optimum point is saying we have material A intersecting with material B. That's our optimum point. Then if we want to find that optimum point, either we can just look at the graph. So here the examiner told us that the point number 3 is the optimum point. So I was just illustrating how they got to point number 3. You have to slide your ruler. The last point to be touched, so you slide your ruler. The last point to be touched is your optimum point. Once you have your optimum point, either you just have to look at what are the coordinates. So we said in most cases, because of the scale that we use on our graph, it's not going to be easy. So what we need to then do is to use simultaneous equations to get the x coordinate and the y coordinate. Then another thing that we need to illustrate here using this graph, we have 2 lines that are parallel to the x-axis. So here it's 1 and another line parallel to the y-axis. So we have this line parallel to the y-axis and the line parallel to x-axis. Those 2 lines, we call them demand constraints. So whenever you have lines that are parallel either to the y-axis or to the x-axis, those are demand constraints. So here, what this line means here, it means that for product L, because here L is the one that is on the x-axis, so here the examiner made a mistake. So this should be L and this should be J. So for product L, there is a demand of 400, that's our maximum, demand of 400. So for L here, the maximum demand here is 400. Then for J, the maximum demand is 450. So remember I said we have resource constraints as well as demand constraints. So in this question we had our resource constraint, which was machine, time, skilled labor, material B and material A. Those are the lines that have different gradients. Then now we have those 2 lines, either a line that is parallel to the y-axis and a line that is parallel to the x-axis. Those are our demand constraints. So here this demand constraint is saying L should not be more than 400. So the maximum units of L that we can make is 400. Then for the maximum units for J that we can make is 450. So that's demand constraint. We cannot make more than 450. It doesn't make any sense. We're not going to be able to sell them to the consumers. So that's it on the graph. So now we're going to continue answering the rest of the question. We continue with the question 123. So we answered the first part. The first part was saying which of the following equations represent the ISO contribution line. So we're looking at a line that is similar to the contribution line. So we had to calculate a contribution of J and then of L. Then we did our step number 3, which is coming up with the constraints. Then we did step 4, looking at the graph. Then we look at the next question here. It says, what is the maximum weekly production for each product? What is the maximum weekly production for each product? So already when I was doing the graph, I answered this part. But I'm just going to repeat. Now, whenever you look in a linear programming and you have a graph, notice that in some cases you're going to have lines that are parallel to the x-axis and lines that's parallel to the y-axis. So you're just saying we're going to have straight lines. Now what the straight lines are here, we call them demand constraints. I told you that we have three types of constraints. We have resource constraints, demand constraints, and policy constraints. Now syllabus mostly look at two, resource constraints and demand constraints. So here with this line here that's parallel to the y-axis, yeah? And for our question, this was L, this was J, this was 400, this was 450. So this line should have been labeled L, this line should have been labeled J. Now what this indicates here is, we're saying for L units, we cannot make more than 400 units because we only have demand up to 400 units. It wouldn't make any sense. If you know your demand with certainty to produce units that are more than your demand, no one is going to buy them. So you're not going to be able to sell them. So we're saying our demand constraint here is we should produce units that are between 0 and 400. We cannot produce negative units. That's always a non-negativity constraint. So whichever question that we do, we always have the non-negativity constraint. Then in other cases now we're going to have the maximum. So here this is the maximum, this is the minimum. So with the first question that we did, we only had a minimum. We're saying we cannot produce negative output, but we didn't have a demand constraint. But with this question, there is a demand constraint which says we cannot produce more than 400 because we're not going to be able to sell them. Then again for J here, for J we're saying we should only produce between 0 and 450. This being the minimum, this being the maximum. So that's what we answered in there. It says what is the maximum weekly production? So for J the maximum weekly production is 450. For L the maximum weekly production is 400. So for J maximum is 450. For L maximum is 400. So that's the second part of question 123. So what you just have to remember is whenever you have straight lines, those are demand constraints. When you have straight lines, then the other lines that are slanting, all those other lines, those are resource constraints. But the straight lines here are demand constraints. So that's on the second part of question 123. Then we look at the third part. It says the maximum amount of material A available is. The maximum amount of material A available. So with this question we were not told how much we have of material A. We're not told how much we have of material A. But what we managed to do is we managed to come up with the constraint. We said the constraint was 2J because we said for J we need 2 cages. Then for L it was 1L or just L. We didn't know the maximum. So we didn't know the constraint. We didn't know how many cages. So that's what the question is asking. It says what is the maximum amount of material A that is available? So how we can get to the answer is, we know that to draw this graph, what they did is, they said if J is equal to 0, what is L? Then they said when L is equal to 0, what is J? That's the easiest way of doing it. So what we're going to do is we're going to go to our table, our graph. So we go to our graph. Now on our graph there we look at material A. Now we can tell with certainty then. So you can tell with certainty that material A is intercepting the y-axis at 450. We can tell with certainty there from the graph. You look at your material A, look at where it's cutting. The y-axis is cutting the y-axis at 450. So we know that at that point, at this particular point, J is 450, then L is equal to 0. J here, it's 450, L is equal to 0. So we replace this into the equation. We say 2 times 450 plus 0 is equal to x. Therefore, x is equal to 2 times 450, which is equal to 900. That's how you get to the answer. Remember, I told you that we will never be asked to draw the graph. But now notice that the way that we will draw in the graph is the way that is going to help us come up with the constraint. So in the exam, you just have to go to material A, you look at 1 point. You just have to identify 1 point. You take that 1 point, you insert the coordinates of J, the coordinates of L. That's how you get your x. So to just see if our answer is correct here, let's go now to the x-axis where we have L. If you go to x-axis, you notice that your material A is cutting the L-axis at 900. So when L is equal to 900, J is equal to 0. So when L is equal to 900, J is equal to 0. So here, when J was equal to 0, L was 450. Now let's replace this to the equation. Say 2 times 0 plus 900 is equal to x. We still get the same answer. Our x is equal to 900. So that's the maximum amount of material that is available. Our maximum amount of material is 900. Means our inequality is 2J plus L should be less than or equal to 900. So I hope you understood this concept. So although you'll not be asked to draw the graph, we need to know how we draw the graph. The graph is drawn by just having 2 points. Say the easy part is when J is 0 and when L is 0. Then if we want to move from the other way, from the graph back to the inequality, we just need one set of coordinates. Either we need here or we need this coordinate. And it's always easy to pick up when one of the x's is equal to 0. It's always easy. With this question, it was easy to notice that when L is equal to 0, J is 450. So that's it on the third part of the question. We're going to now look at the last part. The last part says, which of the following are limitations of linear programming technique? Which of the following are limitations? First one says, linear relationship must exist. So this is true. You notice that we only drawing straight lines in linear programming, so we're assuming that a linear relationship always exists. Then number 2 says there can only be 2 products. So for a syllabus, that's true. We can only have the y and the x-axis. So that's also another limitation. Then number 3 says there can only be 2 scarce resources. That's not correct. We said we can have 2 or more scarce resources. In our case here with 4 scarce resources: material A, material B, skilled labor, and machine time. And number 4, all variables must be completely divisible. So that's another limitation. And number 5, it says a computer must be used to find the optimal point. That's not a limitation. Notice how we did it. We just had to slide our ISO contribution line. That's how we got to the optimal point. So you don't need a computer to find the optimal point. So that's it on question number 123. We're going to look at more questions. We're going to look at a BBP question. So it's question 9.1. The question will come up on your screen. The requirement reads, what is the constraint formula for cotton? Says a clothing company manufactures jackets and trousers. The inputs for the 2 items are as follows. So with the question, we have jackets and trousers. So remember, for linear programming, we're going to have 2 products, jackets and trousers. And the 2 inputs for the items are as follows. We're given, for cotton, we're given polyester, we're given labor. Then we're told that the maximum demand for jackets is 1,000 and for trousers is 500 units. Those are called demand constraints. Demand constraints. So for jackets, so the maximum is 1,000 jackets. So that's a demand constraint. So let's just call jackets J. So we say J has to be between 0 and 1000. Then trousers have to be between 0 and 500. That's a demand constraint. So if we use linear programming, these are going to be straight lines on our graph. So just to show a depiction, say this was J. So if this was J, would be at 1000 straight line. Then T would be at 500. So here this is not asked in the question, but we're just trying to illustrate our demand constraints. And it says, however, this does not include quantities ordered under a long-term supermarket contract for 200 jackets and 50 pairs of trousers. So with this question, we're going to use it to explain the concept of linear programming when there is a contract involved. So in this case, there's a contract where the company is supposed to supply 200 jackets and 50 pairs of trousers. Whenever there's a contract involved, first our resources, we have to give them to the contract. The reason is, if we don't satisfy the condition to the contract, in most cases the penalty will be very high. So first we have to give our resources to the contract, because we're not going to be forfeiting the contract. So our resources first have to go to the contract, then the remaining resources go to the other product. So just repeat that question. Says, however, this does not include quantities ordered under a long-term supermarket contract for 200 jackets and 50 pairs of trousers. The company would have to pay a substantial penalty if this was not satisfied. So that's why we're saying our resources first have to be allocated to the contract. And all three resources are in short supply with maximum availability as follows. Cotton, there's 4,000 meters, polyester 2,000 meters, labor 2,800 hours. There are not enough resources available to fulfill all of the demand and contract units. In order to maximize contribution, the company are planning to use linear programming and need to determine the constraints. So here I'm just going to determine all the constraints, although the question only wants for cotton. But before we determine the constraints, first we need to look at the contract. So the contract is for 200 jackets and 50 trousers. So we want to see how much cotton are we going to use, how much polyester are we going to use, how much labor are we going to use for the contract, because our resources first have to be given to the contract. So for cotton we have 4,000 meters, but first we need to allocate the resources to the contract. So for cotton we're saying 200 jackets are going to take 3 meters, plus the 50 trousers each will take 2 meters. So 200 times 3 is 600 plus 100. So we're saying 700 meters of cotton are going to go to the contract. Then we go to polyester, say 200 times 1.5, which is 300, plus 500 times 0.75. So 3/4 of 500 should be 325. So we're saying 500 times 0.75, 375 plus 300, so 675. So 675 meters are going to polyester. And go to labor. We take 200 times 2 plus, sorry, this was 50. That was a mistake. That was 50. Just repeat that. That was 50. 50 times 0.75. 37 plus 300. 337.5. 337.5. And we're now on labor. Labor, we're going to make 200 jackets. Each one requires 2 hours. and 50. Each one requires 1.5. So that's 400. 400 plus 75. That's 475. So these are the resources that are going to go to the contract. We're going to allocate these resources to the contract. Then for cotton, we had 2,000, we had 4,000 meters. So cotton with 4,000, I'm going to say 4,000 minus 700. It means only we have 3,300. Then for polyester, we have 2,000 meters. So we take the 2,000 meters minus 337.5. Then for labor, we have 2,800 hours. So 2,800 hours minus 475. It's 2,000 minus 337.5. 1662.5. 2,800 minus 475 is 2325. So now these are the resources that the company has to use. Because first we're saying they have to honor the contract. So they have to honor the contract, so these are now the resources that are remaining. Now from the resources that are remaining, now we have to construct our inequalities from the resource remaining. So always remember that if in a question you're given a contract, first our resources they have to go to the contract, then any remaining resources, that's what we're going to use in our linear programming. And we go to our cotton, so our cotton is going to be 3J, because we need 3 meters for every jacket, because 2T should be less than or equal to 3,300. So 3J plus 2T less than or equal to 300. So the answer there is A. If the examiner wanted for polyester, I would say 1.5J plus 0.75T is less than or equal 1662.5. For labor, I would say 2J plus 1.5T less than or equal to 2325. So this would be our step number 3 if we're doing a full question. Step number 3, it's our stating our constraints. So this would be our constraints. Then we would also put our demand constraints. You said so our J cannot exceed 1,000 units. Now T cannot exceed 500 units. So those will be all our constraints. So that will be our step number 3. Then from here we'll draw the graph. So remember, say to draw the graph, we need to say when J is equal to 0, what is T? When T is equal to 0, what is J? And once we have 2 points, we put those 2 points on a straight line. And here we're going to have demand constraints. So we have our demand constraints and we have our resource constraint. So here with this question, they only wanted us to look at cotton, but we just illustrated how we do it if they want it for polyester or if they want it for labor. So that's question 9.1 in our BPP. We're going to now look at another question, question 9.2 in our BPP. The question says the definition of a shadow price is, and say select all that apply. So we're just going to recap on what shadow price is. So first we say a shadow price. We're only going to get a shadow price on the binding constraints. We're only going to get a shadow price on the binding constraints. So in our linear programming, basically it means we're only going to have a shadow price on 2 lines, because our optimum point is always at a point where 2 lines are intersecting. So we're looking at 2 lines. Only 2 lines are going to have a shadow price, and they can have a shadow price only if they are resource constraints. So in some cases, you might have the 2 lines meeting, but one of the line is a demand constraint. Then there's only going to be 1 line with a shadow price. So I'll repeat it. So in a shadow price, we only find it on a binding constraint. On the binding constraints, that's where we find the optimum point. Where we find the optimum point. But with our previous question that we looked at when we were sliding the ruler, our optimum point was when material A and material B were meeting. So it's only material A and material B that could have a shadow price. All the other lines, we call them non-binding constraints or slack resources. We're not fully utilizing them. But these binding constraints, we are fully utilizing them. Therefore, they have a shadow price. And we said a shadow price, we can define it in 3 ways. 1, we said shadow price is the extra contribution that is earned when we have 1 more unit of the scarce resource. The extra part. What is the extra contribution that we earn? Number 2, we can look at the opposite way. Looking at reduction in contribution if we don't have that 1 unit of the scarce resource. Then we talked about the 3rd way, which said is more important. So let's say we're looking at cages that are costing us $10 per kg. So the shadow price now, we can look at it as the premium, or we're looking at the maximum over and above the normal rate. So if our normal rate for labor is 10 kgs and our shadow price is $2, what it means is either you can explain it in the first way of saying if we have 1 more unit of this kg, our contribution is going to increase by $2. Or if we don't have that 1 kg, our contribution will reduce by $2. And the last way we are saying we are prepared to pay $12 for this kg because it's only going to increase our contribution by $2. So we cannot pay more than $12. So on shadow price, we're looking at what premium can we pay on the $10. We can pay a premium of $2 per kg. That's the maximum that we can pay. We cannot pay more than $2 per kg because it's only going to increase our contribution by $2. So then let's look at 9.2. A says the premium that should be paid for 1 additional unit of scarce resource. So that one is correct. The premium that should be paid for 1 additional unit of scarce resource. Then B says the premium that should be paid for additional resources where there is no slack of that resource. The premium that should be paid for additional resources where there is no slack of that resource. So that one B, it's also correct because you can only pay a premium if there is no slack. Because shadow price only occurs on a binding constraint when there is no slack. If there is slack, then there is no shadow price. Then C, so the minimum that should be paid for 1 additional unit of the scarce resource. That's not correct. D says the contribution that can be earned from 1 additional unit of scarce resource. So that one is correct. D. Then E says the total that should be paid for 1 extra unit of the scarce resource. It's not the total, it's only the premium or the extra amount. It's the premium that we should pay for the scarce resource. We're saying if the resource costs $10, we are prepared to pay a premium of $2 over and above the $10. So our answer there will be A, B, and D. It's not the total that should be paid. The answer is A, B, and D. So you should be in a comfortable position to explain shadow price in the 3 ways. So we'll repeat it once more. So shadow price can be explained as the extra contribution that will be earned if we have 1 more kg or 1 more hour. That's one way of explaining. Number 2, saying is the reduction in contribution if we don't have that 1 kg or if we do not have that 1 hour. Then lastly, shadow price is the premium that we're willing to pay over and above the normal rate. So if it costs $10 to buy a kg, we're prepared to pay $2 extra because we know that having that 1 kg will increase our contribution by $2. So that's it on 9.2. So we're going to look at, I think, maybe one more question. For linear programming, we're just going to look at one more question on linear programming, then we close off the topic. We're going to look at question 133. On question 133, it says, which of the following resources will have a shadow price greater than 0? So remember we said we can only have a shadow price at the optimum point. At our optimum point, we're only going to have 2 lines meeting. Those 2 lines are the ones that are going to have shadow prices if they're resource constraints. Here we have our ISO contribution line already drawn, and we're given the possible points as A, B, and C. So we slide our ISO contribution line, maintaining the same gradient. Then the last point to be touched there is B, and the examiner indicated that the point is B. So what we need to look at is, at point B, which 2 lines are meeting? So at point B, we have direct labor hours, and we have a line written R is equal to 500. Remember we say this straight line here, R is equal to 500 and T is equal to 800. We call those demand constraints. On demand constraint, you cannot have a shadow price. So it means that here, we're only going to have a shadow price on direct labor hours because it's the direct labor hour line that is meeting with R is equal to 500. So since these 2 lines are meeting, one is a resource constraint and the other is a demand constraint. We're only going to have a shadow price on the resource constraint. So the only line that is going to have a shadow price is direct labor hours. So I'll just repeat that again, saying we can only have a shadow price at the optimum point. The 2 lines that meet at the optimum point are the 2 lines that are supposed to have a shadow price. But then if one of them is a demand constraint cannot have a shadow price. So therefore in this question, it's only direct labor hours that has a shadow price. So that's it on question 133. We're now going to look at our last question on linear programming, question 135 in the new revision kit. Now for those who don't have the new revision kit, the question will come up on your screen. So in the exam, the first thing that you do is you read the requirement. The requirement says, calculate the maximum amount of material A available in kgs. So in question 135, we have 4 constraints, which are resource constraints. We have direct labor hours, material A, machine hours, and material B. Those are resource constraints. And we have direct labor hours, machine time, material A, material B. These are resource constraints. Then we also have demand constraints. Our demand constraints when you look to the other question, I told you that our demand constraints, we know them because they are straight lines that are parallel to the x-axis and parallel to the y-axis. So if R is equal to 500 there, which is a straight line parallel to the y-axis, and T is equal to 800 parallel to the x-axis. All those lines that are parallel, whenever we have a parallel line, this is a demand constraint. So here we're just explaining again our concept using this question. We haven't started answering the question. But now the question wants us to calculate the maximum material of A that we need. So we're told that the company needs 4 kgs to produce product T, and it needs 2 kgs to produce product R. So it needs 4 kgs of T plus 2 kgs of R. This should not exceed a certain amount. We're going to call X. So already the graph has been drawn for material A. And I told you that to draw the graph, we only need 2 points. The 2 points that we use as easy points, we said when T is equal to 0 and when R is equal to 0. So when it comes to this question, we just need one set of coordinates to be able to find our X here. We just need one set of coordinates. So here we have 2 sets of coordinates. We just need one to be able to find our X. So it doesn't mean that you always have to use when T is equal to 0 and when R is equal to 0. But the reason that we're using it, on this graph, the points that are easy to locate are when t is equal to 0 or when r is equal to 0. So in this question, we first start when r is equal to 0, we go on material A. We notice that the figure is between 1,200 and 1,300. So that's quite difficult to tell. So we don't use that point because it's not easy to locate. Then we go when t is equal to 0. When t is equal to 0, we look at our material A. We notice that r is equal to 1,000. So when t is equal to 0, r is equal to 1,000. So this was easy to identify. When t is equal to 0, r is equal to 1,000. Then when r is equal to 0, we could not easily identify the t. When r is equal to 0, we could not easily identify the t. So now we go to substitute in our formula. So when t is equal to 0, it means 4 times 0, 2 times 1,000. So it's 4 times 0 plus 2 times 1,000 is equal to x. X is equal to 2,000. So when we looked at our step number 3, when we doing our first example, we illustrated how then do we draw the graph. So that was important because now the examiner will give you the graph. They just want you to find the maximum amount. So to find the maximum amount, you need one set of coordinates. You have the t and you have the r, you substitute, that's how you get the x. So that's it on question 135. So now we're going to look at the other theoretical aspects before we conclude the topic. Now we're going to look at surplus. So before we just look at surplus, we just recap on slack. Slack only applies on maximization problem. For linear programming, we said we have two aims. Either want to maximize the contribution, which is the same as maximizing profit, since fixed costs are constant. That's where we have slack. We're not fully utilizing our resources. Then on minimization problems, when we want to minimize our costs, we're going to have what we call surplus. So on our slide it reads, surplus, this is the utilization of a resource over and above a minimum. This is the utilization of a resource over and above the minimum. Surpluses tend to arise in minimization of cost problems. So that's very important. We have to know that surplus arises in minimization problems. Slack arises in maximization problems. And on slack we said, at the point where we have no slack, that's a binding constraint. That's where we have the shadow price. That's where we have the optimum point. So it's very important to remember that at the point where we have an optimum product, or at an optimum point, there is no slack, which means it's a binding constraint. It's a scarce resource. We need more hours of it, or we need more kgs of it, because we are fully utilizing it. So that's it on surplus. The last thing that we're just gonna recap on before we conclude is, we looked at one question where there was a contract. So whenever you have a contract, first of all, you need to satisfy the needs of a contract. First, you need to give your resources to the contract. Then the remaining of the resources, use them in your linear programming techniques. So we call that minimum contractual requirements. So already we looked at a question when a company was making jackets and trousers. They had to first meet a contract where they were supposed to produce 200 jackets and 50 trousers for a company. So first we had to allocate resources to that contract. Then the remaining of the resources, we use it for linear programming problems. So that's it on the theory on linear programming and the computational part. Now we're going to look at the last part, the limitations of linear programming. Now we're going to look at the last theoretical aspects of our linear programming. So in our exam, we should know that the questions that you're going to be asked are not only computative. The theoretical aspect is also as important. So we're just going to recap on a few things. So first, we're going to look at slack. Now slack on our slide, it says, this is the amount of a resource that is underutilized when the optimum plan is implemented. The actual utilization is below a maximum specification. In other terms, slack will occur when the optimum does not fall on the given resource line. But what we call slack resource is the same as what we call a non-binding constraint. We said that we have a binding constraint, and we mentioned that whenever you have the binding constraint, for a syllabus we're going to have two lines meeting. Then those two lines that meet, they have to meet at the optimum point. So two lines meeting at the optimum point, we call them the binding constraints. The two lines that meet at the optimum point, we call them the binding constraints. The other name is, we call them the scarce resource. We call them the scarce resource. So 2 points that meet at the optimum point, we call them the binding constraint because we're saying that they are being fully utilized. So we also call them the scarce resource. And those lines are the only lines that have a shadow price. Remember we said a shadow price, this is the extra contribution by having one more unit of the resource. So we're saying we are fully utilizing our resources. So here, resources are fully utilized. So if we are fully utilizing our resources at the binding constraint or at the scarce resource, we're looking at if we have one more unit of that scarce resource, if we could source one more unit, either of the kgs or the hours, how much would our contribution increase by? That's what we call shadow price. We're just saying, if it was possible to get one more hour or one more kg, how much would it increase our contribution by? That's our shadow price. And we say the other way to explain it then is, if we could get one more of that hour, for example, if we're paying $10 per hour, since it's a scarce resource, it means it might be difficult to get it at $10 per hour. So I want to see what premium are we willing to pay? What is the maximum amount that we're willing to pay over and above the normal rate? So if our shadow price is $2 per hour, which means that the 1 hour is going to increase our contribution by $2. So we're prepared to pay a maximum amount of $2 or a premium of $2. So for this hour, we are willing to pay $12 per hour. We cannot pay more than this, although it's a scarce resource. If we pay more than this, then our contribution is going to reduce. Our aim is we want to increase our contribution because we want to maximize the contribution. So then with the slack resource, we're saying this is a non-binding constraint. We're not fully utilizing our resources. So the question now is, what do we do with those resources? So if you're not fully utilizing your material, you're not fully utilizing your hours, then you can look at outsourcing. You can sell the hours to other departments. You can look at doing other work, doing other projects that require the same type of material or the same type of hours. So that's it on our slide. It says, slack is important because unused resources can be put to another use, e.g. hired out to another manufacturer. A constraint that is a slack of 0 is known as a scarce resource. So the binding constraint or the scarce resource here, the slack is equal to 0. It's a binding constraint. So that's it on the slide on slack. Now we're going to look at surplus. Now we're going to look at the last part on our linear programming, limitations of linear programming. So that's our last slide. So the first limitation says linear relationship must exist. So when we're looking at our linear programming, we only could draw straight lines. So that was an assumption that we have a linear relationship. So that's one of the limitations. We assume that linear relationship must exist. It's not always the case where we have linear relationships. And number 2, it's only suitable when there is one clearly defined objective function. Companies do not operate with only one objective, one clearly defined objective. With linear programming, either want to maximize contribution or want to minimize the cost. So there has to be one clearly defined objective, but it's not always the case with companies. They do not always have one clearly defined objective. In some cases, a company that is entering an industry, they want to maximize revenue, not maximize profits. Then later on, they want to maximize the contribution as well as minimize the cost. So it's not always a clear-cut decision or clear-cut objective. Then number 3, when the number of variables, it becomes too complex to solve manually and a computer is required. We said for our syllabus, we can only handle 2 products because we can draw the x and the y-axis. So then the moment that we have 3 products, now it means that we need a z-axis. Then that's beyond the scope of our syllabus. That's when computer systems are required. So for our syllabus, we can only handle 2 variables, the x and the y coordinate. Then disadvantage for or limitation, it is assumed that the variables are completely divisible. Number 5 says single values, estimates are used for the uncertain variables. And the last one, it is assumed that the situation remains static in all other aspects. So we assuming that everything else remains constant whilst we are maximizing the contribution or minimizing the cost. So those are the limitations of linear programming. So for this topic, you need to know the theoretical aspects. When do we use linear programming? We said we use linear programming when we have 2 products and when we have 2 or more limiting factors. And linear programming has 2 aims. Either want to maximize contribution or want to minimize the cost. On minimizing the cost, how are you going to come up with your optimum pointers? We do the same thing. We need to look at the points here, the points, then we join the points. We join our optimum points. Then we're also going to have an ISO cost line. But now when we slide the ISO cost line, unlike when we did it for the ISO contribution line, we're looking at the first point to the last point to be touched. But now if it's the cost minimization problem, we're looking at the first point to be touched. So we're saying the first point to be touched. That will be the optimum point, the first point that we have to touch. So you can try some questions at the end of chapter, questions on minimization of cost. Then you also try questions on maximization of contribution. So that brings us to the end of linear programming.